Howdy team, welcome back to my latest video on computers and digital circuits in Duck Game. Today I'm going to introduce you to latches and registers. So what is a latch? A latch is just a digital switch. You have two inputs, on and off, or set and reset, and an output. If set was the last signal that was turned on, then the output is on. If reset was the last signal that was turned on, then the output is off. I can demonstrate that to you right here. I have a latch right below me. So the side I'm currently sitting on is the set. I'll press that. What happens here is the block falls down here. We'll call these buttons the output. And so right now it's on, and regardless of what I do on the set signal, the output stays on. Turn it on, off as much as I want. The output of the latch stays on only until I hit the reset signal. And now it turns back off. And similarly, I can do whatever I want at the reset end. Nothing's going to happen until I turn on the set signal here. So all that's going on a latch is you have either two NAND gates or two NOR gates. This is a NOR gate design. And then the outputs the output of each gate feeds into the input of the other one. So here we have a NOR gate. These buttons are the output of that NOR gate, and following this wire, it feeds into the input of this NOR gate. And here, this NOR gate, this is the output button, feeds in through this repeater to the input. See here, the crate trajectory feeds into these buttons, which is the input of the other NOR gate. Now, you can also build this out of NAND gates. Down here is a much smaller latch that I made with one of the designs featured in my last video. I didn't necessarily explain it, but it's in the map download if you want to play with it. And this is made out of NAND gates, so a latch circuit fundamentally is symmetrical. If we could cross over wires in Duck Game, then I could very easily just have this wire here and then have a wire coming out here and going into this input, but we can't. So we have to add this repeater here. But fundamentally, the circuit is symmetrical. So which side is set and which side is reset, and which output of the logic gates you want to use as your output of the latch is ultimately up to your design. It's very arbitrary. You can define it however you want. Maybe you need to invert an input or an output. You change it to suit your situation. Here we have a NAND gate based latch, and NAND gate based latches work a little bit different, as in if you want to think about them the same way, you need to invert the inputs. So that's exactly what I've done here. Just an inverter on this NAND gate's input, and here's an inverter on this NAND gate's input, and I can show you how it works here. So this is my reset side. I can jump on my reset. Nothing about the gates changes until I hit the set. Now it changes, and nothing I do here matters until I hit the reset. Now, latches are actually pretty useless by themselves. Thanks to something called metastability. So I can demonstrate. So when you turn on a digital circuit, like a real physical digital circuit, likely what happens is both inputs get powered at the same time. And since the circuit is symmetrical and also a loop, we have a problem here. As soon as I load the map, these blocks will fall in the inputs. And then, because this block falls in this input, this logic gate is going to change its state, and it's going to change the state of the second logic gate. At the same time that that's happening, the block here is falling on the input of this logic gate and changing the output of the other logic gate. So they're going to be looping back and it's a feedback loop. And I can show you exactly what it looks like here. When I load the map, you see here, it's just going to indefinitely keep spazzing between the two until I choose one side, either set or reset. And this is pretty useless in a digital circuit sense because it's unpredictable. We want everything we do on a computer, on a digital circuit, to be perfectly predictable. Otherwise, we can't expect it to do anything as we intend it to. So, and you can actually see this when I load the map. This also happens on the latch above. Although thanks to the delay on the repeater, it does eventually resolve. This is much more how it would look like, I guess, in a real sense. Eventually it will resolve. It's just unsure how long it'll take to resolve and which side of the latch will be on when it resolves. So we can fix this. We just make sure we're not blowing our ears out with constant looping here. In a digital circuit, the way you'd end up fixing this is you would tie all your latches to a reset signal. you would assert this reset signal as soon as you turn on your circuit so that it forces all your latches across your design into a default state. Now, another thing that'd be useful to do with latches is to be able to control exactly when we're looking at when it reads the inputs to change the output. So if you add something like that, what you get is called a register, which is fundamentally 1 bit of memory. Here above me is a register. The register has 3 inputs. It has the reset, as we mentioned earlier, which just forces the latch to output a default guaranteed state. And we have our data input, which is effectively both the set and reset tied together to the same input. Just that same input is inverted for one of the two sides, whether it be the reset or the set. And then we have our clock signal, which enables the latch to read what's going on the data input. So here I can show you how it works. The output is all the way down here, this button here. If there's a block on it, the output is on. If there's not a block on it, the output is off. And so because I can now control exactly when the latch reads the input, I can do whatever I want on the input. And nothing is actually going to propagate through to the bottom until I hit my clock input. So right now my data input is on, and now I'm going to hit the clock input, and you see eventually propagates down to the bottom, and the entire register turns on. The output is on. And now, as long as the data input is on, every time I clock it, it'll read that and say, oh, it's still on. Okay, I'm going to keep the output on. If I remove the data input, the output of the register is going to stay on until I mess with the clock. So right now, you see at the bottom it's on. Here I hit clock, and now it finally turns off. So yeah, effectively 1 bit of memory. I have the input, and whenever I assert the clock signal, the register reads the input and copies it to the output and keeps it there until I change anything with the data input and then clock that as well. We also have the reset signal, which, as mentioned earlier, just guarantees that the register is in a default state. Here, let me turn it on. And now if I hit my reset signal, it just forces it off. And if my register is already off, when I hit the reset signal, it just keeps it off. Now this, the way this sort of a register works in terms of logic gates is here we have our a NOR latch. You can see this looks very similar to this over here. You just remove the buttons. The reset just connects to one end of that NOR latch to guarantee that it's in a specific state. And then we have 2 AND gates up here. So both inputs of the AND gates are tied to our clock signal or our enable signal. And so when that clock signal gets asserted, half of one side of both of the AND gates will open up so that whatever happens on the data end can freely propagate through to the registers. The data end here, as mentioned earlier, it connects to both inputs of the latch going through these AND gates. And just one side is a direct connection and the other side passes through an inverter. Now, this register was my very first design, just to make sure it works. It's clearly very big and also very slow. Here's an example of what I've tried to do optimizing it. Thanks to De Morgan's law, which I mentioned in my previous video, by inverting some inputs, outputs, and also signals within the register, we can swap around what kind of logic gates we're using to potentially simplify and reduce the size of a design. So in this case, our register is built out of 2 NOR gates and then 2 AND gates and an inverter. Here we have a register built out of 4 NAND gates and also an inverter. And so if you compare here the time of, just to reiterate, show you how long it takes for a signal to propagate through this big register. I hit the data and now I hit clock. 2, 3, yeah, it takes about like 2 seconds or so. If I come over here to this latch, I hit the data and then I clock. It takes about half a second to propagate through. Now, just a small feature to note, anytime you use a register, you turn on a circuit, you always want to assert the reset at the very beginning to ensure that everything's in a default state. Very simply here, I have my reset button, and I also have a spawn cannon that just shoots a dueling pistol into it and sends the dueling pistol through a fun beam to immediately unload it so that it just immediately slaps the button and despawns. A second or so after I load the map, you can Watch it closely. There you go. Now the circuit is reset and ready to go. And yeah, so this is a register and it operates much faster. See right now the output is off. I mess with the clock signal, nothing changes until I turn on the data. There we go. Now the output's on, and if I want, I can turn off the data. Output's still on. I clock it. Now to show everything. Right now the output is on. I can hit the reset, and it turns off again. So that's about all there is to it. If you remember from my last video, I talked about a background in Minecraft. Building registers in Minecraft is very, very simple because of a glitch called piston quasi connectivity. You don't need to know anything about how that works, but fundamentally in Minecraft, that means we can basically use a single piston to mimic the functionality of a register. One piston, which in Minecraft is a single block. We can build a register out of a single block. From that frame of reference, you can understand maybe why I find it so frustrating when I see my registers here that are enormous. Now, registers are pretty complicated contraptions, so it's like, okay, maybe it's all right that it's big. If you think about your computer, a register is a single bit of memory. Your computer, first of all, memory-wise, probably has gigabytes of, I hope has gigabytes of RAM, which is going to be millions of registers. And, okay, we're not trying to build a fancy AMD processor with a bunch of extra RAM sticks strapped to it, but even then, think about your computer. It's 64-bit. If you have a really old computer, it'll be 32-bit. What does that mean? It's that all the data is processed in the computer 64 or 32 bits at a time. So if we were to design that in Duck Game, we would need 32, at the very least, 32 of these registers here in parallel for every bit where we need to store a number for a given time. That's going to scale up really fast. Duck Game maps are not infinite. So the size of our register, which is more or less influenced by the size of our logic gates, determines very much how big and complicated of contraptions we can produce. So this issue led me to looking into other ways to design logic gates. If there was maybe any sort of glitch I could take advantage of in Duck Game that kind of functioned similar in Minecraft, where there's a weird glitch that causes a block to operate like a register. And so that will then lead into my next video, where I'm going to show you a much smaller design that I came up with for logic gates. So that's about everything. Thanks for watching. I'll see you guys next time.